Something happened on the ocean floor yesterday that most people completely missed, not because it was hidden or because agencies were keeping it quiet, but because the signals it sent don't show up on your phone as a breaking news notification. They don't shake your walls or knock things off shelves. They travel through rock, water, and pressure gradients, heard only by those watching lines move on screens in government buildings. In the final hours of June 3, 2026, the seafloor roughly 154 kilometers off the southern coast of Oregon released energy, a magnitude 5.7 earthquake. It happened at 10 kilometers depth, out in the deep Pacific, far enough from shore that nobody in Crescent City felt it. Nobody's phone buzzed. There was no panic and no news trucks. The USGS classified it green, meaning minimal expected damage and casualties, and moved on. That's the correct classification for an offshore moderate earthquake. But a green alert and nothing to worry about are not the same thing, and that distinction is at the heart of what we need to talk about, because the 5.7 wasn't alone. In that same 24-hour window, 6 more earthquakes above magnitude 4.5 fired off in the exact same stretch of seafloor. A 5.1 west of Petrolia, California. A 4.48, then another 4.48, both clustered just offshore. A 4.5 recorded by the European Mediterranean Seismological Center in the early hours of June 4th. 7 earthquakes. 1 narrow corridor. 1 day. And not in some random stretch of open ocean, in one of the most geometrically extreme locations on the entire surface of the planet. It's called the Mendocino Triple Junction. It is the single point on Earth's surface where 3 separate tectonic plates come together at the same address. The Pacific plate arrives from the southwest, grinding northward along its long, relentless path. The North American plate sits to the east, slowly warped along its western edge by forces it can't resist. And from the north, diving downward at an angle, comes a third plate, smaller, older, and dying, the Gorda plate. What remains of a vast oceanic plate system called the Farallon. The Gorda is being squeezed from the west by the Pacific, shoved beneath North America from the east, and pulled apart from below by an active spreading center. 3 plates, 1 point, and no possible resolution that doesn't involve enormous ongoing force. Every earthquake exists because these rigid pieces of crust refuse to yield. Directly north of the junction runs the fault that changes everything, the Cascadia Subduction Zone, a 1,000-kilometer-long megathrust system stretching from Cape Mendocino to British Columbia. This is where the Juan de Fuca plate, the Gorda's larger sibling, dives beneath the North American continent, accumulating massive amounts of strain. Seismologists treat one date with reverence, January 26, 1700. The last time this fault ruptured in a full margin magnitude 9 event, sending a tsunami across the Pacific. Waves arrived in Japan with no local earthquake to explain them. Centuries later, researchers like Brian Atwater matched Japanese records to ghost forests on our coast, pinning the event to that winter evening. This research established that Cascadia has done it before, and the clock has been running for 326 years. This fault is not just a hazard, it's a historical certainty. Chris Goldfinger and his team at Oregon State University spent over a decade pulling sediment cores from the ocean floor, cataloging turbidite deposits, layers of sediment disturbed by underwater shaking. They built a record of past Cascadia ruptures going back 10,000 years, finding 43 major events. This gives us a mean recurrence interval of roughly 525 years. But the variation is enormous. Some events recur within 200 years, others take 800. At 326 years since the last rupture, Cascadia sits in the middle of that distribution. It's not overdue in a dramatic sense, but we are in the mature phase, the loaded phase, where the question isn't if, but a conversation about the stacking of probabilities over time. The Cascadia Fault is not a single uniform structure. It has a southern segment, closest to where those 7 earthquakes just fired off, that has a documented ability to rupture independently, producing a partial rupture at magnitudes between 8.1 and 8.2. This would be one of the most destructive regional earthquakes possible on the West Coast, causing 3 to 5 minutes of violent shaking across northern California, southern Oregon, and inland into the Willamette Valley. A regional tsunami would follow, with waves up to 15 meters high arriving while the ground is still shaking. There is no alert system fast enough. The shaking itself is the only warning. The published probability of that southern segment rupturing partially in the next 50 years sits at approximately 37%. That is meaningfully higher than the 10 to 15% probability assigned to a full margin event. The monitoring data right now is not quiet. Underneath the Cascadia Subduction Zone, There is a zone of rock that sits between the locked seismogenic zone, the brittle upper fault, and the deep creeping zone below. This middle zone, called the transitional zone, doesn't rupture violently. Instead, it releases strain through a slow, silent process. Slow slip events, occurring so gradually that no ordinary seismograph would detect it. This phenomenon was first formally described in 2003 when Herb Rogers and Gary Draggart of the Geological Survey of Canada published a paper in Science titled Episodic Tremor and Slip on the Cascadia Subduction Zone, the Chatter of Silent Slip. What they had noticed was a recurring tremor signal beneath southern Vancouver Island, appearing roughly every 14 months, coinciding with tiny reversals in the GPS surface deformation data above. The island was briefly moving in the opposite direction it normally does and then snapping back. The deep interface was slipping, slowly, silently, and on a regular schedule. Each of these slow slip events transfers a small stress increment between 1 and 10 kilopascal onto the locked seismogenic zone directly above it. This is tiny compared to the megapascals released in a megathrust quake. No single slow slip event triggers a rupture on its own, but at a recurrence of roughly every 14 months over 326 years, the cumulative loading from an estimated 240 such events is not trivial. Relative to the total strain budget the locked zone is carrying, these quiet episodic slips are part of the mechanical story of how Cascadia loads between major events. In the same 24-hour window that the 7 earthquake cluster lit up the Mendocino corridor, the seismic stations of the Pacific Northwest Seismic Network log something else: elevated non-volcanic tremor counts beneath the southern Cascadia margin. Roughly 50 tremor epicenters in one day, meaningfully above the long-term ambient baseline. Not by an order of magnitude, but enough to be flagged by researchers. Enough to be reviewed by people whose entire careers are built around interpreting what that signal means. The data was whispering, and the experts were listening. What the monitoring data is showing, with high probability, is an active slow slip episode in the early stages of its evolution on the deep transitional zone of the southern Cascadia margin. And the locked zone immediately above that slow slip sits directly above the corridor that just produced 7 moderate earthquakes. These two observations are almost certainly coupled. The offshore earthquake cluster is the surface expression of the stress that the slow slip is delivering from beneath. The system is talking to itself in the only language geology has: pressure, movement, and time. Before we go further, 2 things circulating online deserve to be put to rest. The claim that a solar storm on June 3rd triggered this cluster is false. Seismological consensus is clear: solar activity does not trigger earthquakes. The proposed coupling mechanisms operate at energy levels many orders of magnitude below what's required for fault rupture. The timing is logged, but it is not causal. Second, a tsunami warning that appeared in some feeds was a data artifact. There is no active warning. The cluster events were not tsunami generating, and the official architecture has not issued a warning. Now, about the 7 earthquakes themselves, there's one technical nuance worth explaining. All 7 events are currently listed at 10 kilometers depth. That uniformity is not a measurement result, it's a default. The USGS algorithm assigns 10 kilometers when offshore station coverage isn't sufficient to constrain the depth. The actual depths vary across the upper 20 kilometers, consistent with the 2 dominant fault mechanisms at the junction. Strike-slip motion along the Mendocino Transform to the south, and shallow oblique thrust faulting on the Gorda Plate to the north. Until formal solutions come back, the depth numbers tell you to hold your conclusions. The 5.7 is particularly interesting. Its position places it at the northern end of the corridor, where the Gorda Plate interface transitions into the southern Cascadia subduction structure. If the formal moment tensor solution confirms shallow thrust faulting on that interface, then the 5.7 would represent a small piece of the actual subduction interface slipping, the geometry that connects directly to the Cascadia locked zone. That is a meaningfully different reading than if the dominant mechanism turns out to be purely horizontal transform-type motion. The experts are watching these solutions closely. The shape of this event sequence is worth paying attention to. A standard earthquake sequence looks like this: one main shock followed by a decaying tail of progressively smaller aftershocks. The rate of that decay follows a statistical relationship called Maury's law. What happened on June 3rd does not match that pattern. There was no single dominant main shock followed by a clean decay. There was a distributed sequence of comparable magnitudes spread across time and across a 150-kilometer-long corridor. The 5.7 was the largest, but the remaining events were not organized around it in an aftershock geometry. They were spread in space and comparable in magnitude. This pattern is called a swarm, and swarms behave differently because they have different causes. A swarm is typically driven by an aseismic process, fluid pressure changes, or, at subduction zones, slow slip on a deeper interface that doesn't itself rupture the surface but incrementally loads multiple smaller fault patches until each releases on its own schedule. The swarm is the symptom. The slow slip beneath is almost certainly the cause. So where does all of this leave us? What are the realistic scenarios from here? The most likely outcome, the conservative reading, is that the cluster activity decays back to background over the coming days. The system returns to its long-term ambient state, as it has most of the time in the past. The middle reading is that the stress transfer from this slow slip episode has incrementally shifted the conditional probability of a southern segment partial rupture, not dramatically, but by a real and trackable amount. The seismological community watches that shift because small shifts compound. The aggressive reading, the one that justifies current monitoring, is that this cluster is a precursor sequence. Stress delivered now may be early-stage preparation for a partial rupture of the southern Cascadia segment within a window of days, weeks, or months. The probability share on that reading is small, but it is not zero. And in seismology, not zero combined with magnitude 8.1 to 8.2 on a fault directly underneath millions of people is the configuration that keeps scientists watching their screens late into the night. What to track if you want to follow this story as it develops? Look for continued non-volcanic tremor activity in the Pacific Northwest Seismic Network's episodic tremor and slip catalog beneath the southern Cascadia margin. Watch for additional moderate offshore events in the Mendocino corridor. Watch for any updates to the GPS surface deformation data from coastal stations in Northern California and Southern Oregon. A reversal in the deformation trend would be a strong confirmation that slow slip is actively underway. And watch for the formal moment tensor solutions from USGS as they come in. If those confirm thrust faulting on the subduction interface, the interpretation changes in an important direction. The fault has been loading for 3 centuries. The people whose job it is to watch it are watching it more carefully this week than they were last week. That's the story. Not panic, not certainty, but the most observable signal the system has sent anyone in years, and the people who know how to read it are paying close attention. We'll be tracking this as it develops.